Okay, folks, in the second part, part two, I guess, I'm going to keep working with linearization. So here I've given you the steps for doing linearization, and so I'm going to apply these steps to the next two problems. So I'll let you pause the video and read through them. Okay, so we're asked to use linear approximation to evaluate e to the negative 0.15. So we want to get a decimal approximation on this value, and we don't want to use this function. Remember this, the beauty of this tangent line approximation, this linearization, is it enables us to get a solution that's going to be very close to this without actually using the exponential function. Instead, we'll just be simply using multiplication and addition by computing points on the tangent line. So step one in this bullet point said to give a function that mirrors the desired operation. So what function will look like the operation that I'm trying to do here, which is evaluate e to this particular power? The function that I want to pick is f of x equals e to the x. Okay? And then the question is well, where do I want to center this linearization about? So this is what I've been calling the anchor point. And the anchor point should be a point that's easy to evaluate in the original function. But the other thing is it needs to be close to the point that we want to evaluate. So our goal, then, based on how we've given the function here, is we want to know what is f of negative 0.015. That's our goal. So I want to pick a point that's easy to evaluate in the e to the x function that is also close to this negative 0.015. So pause the video for a moment and think about what that a value should be. So we want to center this at a equals what? So go ahead and pause the video and decide where we should be centering this linearization at. So we want to center this linearization at a equals 0. That is, f of 0 is easy to evaluate in the function. So y? 0 is easy to evaluate in f of x. Okay. And 0 is close to negative 0.015. Okay, folks, this second step here where I say pick a point that's easy to evaluate, that's for doing the problems in this class. In the real world, the way you would think about it is you would actually collect a data point. In this case, you'd figure out what the ordered pair is with data for when x is 0. You'd find that data point. You would calculate the rate of change at that data point by some means, and then you would construct a tangent line to then extrapolate other values looking into the future. But in this class, in order to answer these questions, you're going to pick your point the way I just described. That it's got to be easy to evaluate in the desired function and close to the point that you're trying to evaluate. Okay. So now actually let's build the linearization. Okay, so L0 of x in this case, well, that's still going to be just the tangent line, so that's f prime of 0 times x minus 0 plus f of 0. Of course, I could simplify things like this x minus 0, but I want you to see that this is just that linear approximation that we talked about on the previous page. It is just this, let's see here, it is just this linear approximation right here. Let's see, oops, wrong page. Still wrong page. Okay. So in order to use this linearization, we need to figure out what f prime of 0 is and what f of 0 is. Well, our function, we said, is e to the x. So what is f of 0? That is e to the 0, which is 1. And what is f prime of x? Well, this is a particularly straightforward one to take the derivative of. And then, so what is f prime of 0? It is also e to the 0, so it is also 1. So that means our linearization centered at 0, the tangent line that we're going to use is 1 times x, and I'll keep writing x minus 0 here, plus 1. Okay? Folks, the picture that I want you to see for this is that if I gave you the function e to the x, so here's the graph say, of e to the x. That's not very exponential. It should be rising a little more steeply, but you get the idea. And if I said, hey, I want to evaluate this function right here at negative 0.015, how are we going to do that? This is our strategy. So what we do is we come up with the tangent line at a point that's easy to evaluate. That's our anchor point right there. That's the ordered pair 0, 0, right? So we built this the green line here, I should have done it in green, is the tangent line in red right here. Okay. And so rather than plugging negative 0.015 into the orange function, which is hard to do, we're going to plug negative 0.015 into the line and get a decimal approximation on it. And you can see that the y values of the point on the function and the point on the line, although my picture's a little bit makes them look a little bit far away, they're pretty close to one another. Those y values are close. So that's the idea of this procedure. Okay, so we get that L0 of negative 0.015 is equal to 1 times negative 0.015 minus 0 plus 1, which is negative 0.015 plus 1, which is about 0.98, well, which is, let me not say about, which is 0.985. Okay. So again, what we said is that this point, the y value on the red line here has a y value of about, or a y value of 0.985. And let's compare that to the actual value. So the actual value, that's tiny, so hoping that to be bigger. The actual value is about 0.98511, and so you can see, again, we're accurate in this case to within 1,000th of the true answer. Okay, so folks, what I'd like you to do now is pause the video, and I want you to go ahead and try number 8 on your own, where I'm asking you to use linear approximations to evaluate the fifth root of 33. So go back to the steps from the previous page. Sorry, getting motion sickness here. Go back to these steps, number 6, go back to these steps on the previous page and try to replicate this. So pause the video and give this a shot. Okay, so picking up with this, the first step in our bullet point was to come up with a function that mirrors the operation. Okay? So the function that mirrors the operation is the fifth root function, the fifth root of x. Okay? So the next thing I want to do is choose my anchor point, and this is where I find most students have trouble in deciding the anchor point. Most students have said, oh, I know, the fifth root of 32, that's 2. Which of those two numbers, 32 or 2, is your anchor point? Well, our anchor point, A, is going to be 32, the value that we're going to plug into the function. That's easy to evaluate in the function. Okay, so that's our anchor point. So then we're going to find the linearization about 32. So this is equal to f prime of 32 times x minus 32 plus f of 32. So again, all the linearization is a function, is the tangent line of the curve that's anchored at 32. So I'm not entirely sure what this fifth root curve looks like. Maybe it looks something like this. Okay? And our goal is we want to know what the fifth root of 33 is. We want to know what is this y value right here. But instead of plugging into the function, what we're going to do is we're going to build a tangent line about 32 that approximates the curve. And you can see from my graph here that the orange line approximates the blue curve, and that means that when we plug 33 not into the blue curve but into the orange line, we're going to get y values that are similar to one another. So this is the this equation right here is the equation of that orange line based on the picture I just drew. Okay, so what do we need to do to be able to evaluate this? Well, we need to figure out what f of 32 is. Well, f of 32 is the fifth root of 32, which is 2. Then we need to find f prime of x. What's f prime of x? F prime of x would be 1 over 5 times, oh boy, I just forgot how to do this. times the fifth root of x to the fourth. Okay. Let me just double check that, folks. So let's check that using the power rule. So let's see here. If we have f of x is equal to x to the 1/5, its derivative is 1/5 x to the minus 4/5, which we could write as 1 over 5 x to the 4/5, which I could write the way I did. There's nothing wrong with what I wrote. I could write it as the fifth root of x to the fourth, but I think it's going to be better to give this formulation of the derivative to say that it's 1/5 times the fifth root of x raised to the fourth power. So instead of taking 32 to the fourth power and then the fifth root, I'd rather take the fifth root of 32 and then raise it to the fourth power. So that's what I'm going to do here. So we get that f prime of 32 is equal to 1 over 5 times 32 times the fifth root of 32, all to the fourth power. So that's 1 over 5. The fifth root of 32 is 2, so we're left with 2 to the fourth power. 2 to the fourth power is 16, and so we get 1 over 80. So now we know both what f of 32 is and what f prime of 32 is, so we're ready to plug those two values into our linearization, and we get that L of 32 of x is equal to 1 over 80 times x minus 32 plus 2. So now I'm ready to approximate the fifth root of 33. Oh, excuse me, this is still anchored at 32. So we're going to plug 33 into our linearization. That is, in terms of the picture here, I'm going to plug 33 into the orange line and say that its output is very close to the fifth root of 33. So I know that sometimes this gets lost on us as we're working through the calculations. Notice that once I built my linearization, once I have this function right here, the only thing I have to do in trying to determine what the fifth root of 33 is do some subtraction, some multiplication, and some addition. That's far easier than actually doing the fifth root operation. Okay, so we get 1 over 80 times 1 plus 2, so we get 1/80th plus 2. Let's go ahead and get those as a single fraction. So it'd be 1 over 80 plus 160 over 80. Which is equal to 161/80ths. And 161/80ths represented as a decimal is 2.0125. And what is the actual answer? So it turns out that the actual answer for the fifth root of 33 is roughly 2.01235. So a little bit off. We're accurate to the thousandths place, but a little bit off for the digits beyond that. Still, this linearization is a decent approximation to actually calculating the fifth root of 33. So again, I want to zoom in on that curve one more time. So if this is my axes, here's the let me do the axes in blue or a different color. Let's do the axes in green. Okay, so here is my fifth root of 32 function. Okay, I'm drastically exaggerating it just so we can see what's going on. At 32, we built the tangent line there, and so our tangent line, yeah, it's just okay. Let's try that again. We built the tangent line. The tangent line is given by this function right here. The equation of this line is y equals 1 over 80 times x minus 32 plus 2, but we're just going to call this, instead of calling it y, we're calling it L32 of x, linearization anchored at 32. Okay. So our goal was to determine what is the fifth root of 33. Okay. Well, the fifth root of 33, we said down below here, it's approximately 2.01235. And rather than finding that, what we did was we found L of 33. And we said that L of 33 is equal to 2.0125. And the idea is that, yes, there is a little bit of a distance between those two answers, and you can see that they're not quite right beyond the thousands place, but that is close enough. That's what we mean by a linear approximation. So this is the last linear approximation I'm going to do. Now we'll look at differentials.